Hello everyone, welcome to the platform of Unacademy, India's largest learning online platform. So I welcome you all. Okay, so audio video is good. So welcome to the platform of Unacademy, which is India's largest online learning platform. So this is a brief introduction about me. My name is Vidyapati Kumar, and I have a 4+ year of teaching as well as research and development experience. I have done ME from Jadavpur University. I have worked at CSIR Central Institute of Mining and Fuel Research for about 2 years and qualified GATE twice. I'm the author and co-author of several research papers, and you can Google about me and find more details about my papers if you have a keen interest about that. Okay. So, hello Nani, hello Ashish, hello Indrajit, hello Mukta. Good evening. Good evening to everyone. So, this session would be more specifically will be inclined towards tool wear. We are going to see the tool wears. What are the tool wears that we encounter during the machining process, as well as we are also going to see the tool life, how we are going to predict the tool life, and what are the parameters on which this most important thing is dependent upon. So you can download the Unacademy learning app because it is really worth it. I'm taking the strength of material in this learning app, and I'm going to complete the strength of material entire everything in this app only, focusing for the GATE and ESE preparation. So if you are aspired for this preparation, please go and download this and attend my classes, and you will be benefited with this. There are a lot of benefits of this an academy learning app. That is, daily live classes are there, structured courses are there, as well as you can give a lot of tests and quizzes which you have the unlimited access. This is the most important thing, you can access like. Okay, so if you are planning for a plus subscription, you should use the plus subscription because it is very in nominal price. An academy is offering the plus subscription, as well as it has a daily live classes. You can attempt a lot of live classes from the top educators, and these are in structured courses, as well as complete coverage of the syllabus would be there, as well as daily tests and quizzes are there. You can go and attempt with there. So in case these are the top educators of the Unacademy, and in case if you are planning to purchase the Unacademy plus subscription, then it would cost around 12 months 25,000, and if Sir VK, then it would cost around 32,500. So you are getting the 10% off in this Unacademy plus subscription. There are a lot of things like 3 months plan is also there, 6 months planning for a short term. Then you can go for the free plan. You will get the 10% off if you would use the code SIRVK. And similarly, for those students who are in second or third year, they can opt for a 24 months plan, and this is around 30,000. But if you use my code, then you will get a 10% off, and this would be around 27,000. So approx like 37 rupees per day you have to invest in your. So this is what is this thing. Okay, Asis has some doubts. What are the doubts you have, Asis? Can I have metallurgical engineering classes? Ramesh, the classes that I give is basically focused for the mechanical engineering. I will take the material science, but For the metallurgical engineering, for specifically for the metallurgical engineering, I cannot give the classes. Assis has told sir, while calculating radial forces, somewhere you told that it is 0 in orthogonal. Radial force. Okay. Okay, so what happened? Okay. See, thrust forces. See, Assis, I understood your problem. See, Assis, whenever we are using in turning operation, see, turning operation is generally three types. Okay. Turning operation is generally three types. That is uh, three types of forces are acting. Okay. So first is your cutting force, and the two components of the thrust force are acting. That is, the first component is axial force, as well as the second component is the radial force, right? Radial force. So even if the radial force is zero, you have one component of thrust force, that is axial force, that is always comes into the picture. Okay. Ramesh, for if you are planning for the subscription, then you have the for 24 months it would cost around 30,000. But if you will use my code SIRVK, if you will use my code SIRVK, then it will cost around 27,000. And this 27,000 includes everything from GATE to ESE, both, right? It will cover both the things. So if you will see per day calculation, if you do the per day calculation, that would be around 37 rupees per day. And these are the charts for 1 month, 3 months, 6 months and 12 months. So in every prices you will get a 10% off if you will use my code. Okay. And assist your doubts is clear or not, let me know. Yes, Ramesh, this is about the plus subscription. This is about the plus subscription. So shall I start my new topic for today's topic? Okay, Asis, I'll clear at the end of the lecture. Okay, just remind me. So today what we are going to see is the tool failure. Okay, now see what happens that when we are machining, then chip flows from the surface of tool, right? Chip flows from the surface of tool, and due to a lot of time, like time of machining is more, or what part of workpiece you are machining, these things depends. So based upon those things, the tool life decreases. Tool life decreases. Okay, so tool life decreases, and hence a time will come when tool gets failed. Okay, tool stops serving its purpose, tools get fails, right? So there are two types of failure, like there is a slow death and there is a sudden death. Okay, now what is the difference between them? The difference between them is, sir, you already know that if this is the side view of the cutting tool. Okay, and what is this, sir? And what is this? Can you tell me? Name the surface. Name the surface. Tell me in the comment box. Surface 1 का नाम क्या है और surface 2 का नाम क्या है? Tell me the name. Tell me the name of surface 1 and surface 2. I'm waiting for your reply. Okay, see, surface 1 is actually rake surface, okay? First is rake, okay. Okay, thank you. Good participation is there. So first surface, this is known as rake surface, and this is what? This is known as flank surface. Okay, this is flank surface. Clear? So what happens? What happens that uh, when we are machining, so suppose the tool, the chip flows like that. Okay, the chip flows like that. Okay, so suppose this is in this way the chip is flowing. So what will happen? Chip will try to erode these things, erode these part. Okay, this part of the cutting tool get eroded, and sometimes this flank surface is also get eroded, right? So there is the gradual or the progressive wearing, the gradual or the progressive wearing away of rake surface. In rake surface, when there is a gradual wearing, this gradual wearing in rake surface is known as crater wear. Okay, so whatever the wearing will be in our rake surface, that is known as crater wear. And on the flank surface, whatever the wear and tear of the tool will be on the flank surface, that is known as flank wear. Okay, flank wear. So these two are the slow death. Why slow death? Because by varying the velocity, by varying the machining time, so these things are relatable, and due to these things the failure takes place. Fine, but there are some of the sudden death. What is its meaning? Sir, failures leading to premature end of the tool. The sudden death type of the tool failure is difficult to predict. So suppose that you are machining and all of a sudden the tool get fail. And what is the reason behind it? It is very difficult to predict the sudden failures, right? So tool failure mechanisms include plastic deformation, brittle fractures, fatigue fracture, or edge chipping. However, it is difficult to predict which of these processes will dominate and when the tool failure will occur. So we cannot monitor, we cannot predict the sudden failure, but yes, we can predict the slow failures, which are actually progressive, which are actually gradual, and which we can see from our naked eye. Okay, so these things are important for us. Now let's move to the tool wear. Let's move to the tool wear. So this is the tool wear. So basically tool wear is of three types. What are the types? Flank wear, crater wear, and chipping of the cutting edge. Chipping of the cutting edge. So you know, in a tool you have a cutting edge. What happens sometimes that during the machining, the cutting edge, the part of the cutting edge get chipped off, get removed. Slightly the part of the cutting edge get removed and veered out from that part. So that is known as chipping of the cutting edge. And see what happens. What happens that what is the crater wear? See, this is your flank surface. Clear? This is your flank surface. So what happens on the rake surface? You will find something like that. Okay, so you can see here your rake surface. Here your rake surface is having a lot of deformities, right? A lot of wear. So you can see tool get weared out from the rake surface. Similarly, for the crater, for the flank wear, the flank part of a tool get weared out. Okay, this is the flank part which get wear out. Fine. So this is how the tool wear. Generally tool wears we have seen, generally the tool wears are only flank wear and the crater wear. This is the two general things that you have to study for a gate. So you know that what is the chipping off of the cutting is, I have already explained you. So now let's analyze these two wear, flank wear as well as the crater wear. Okay, so I have already told you what is the flank wear. Okay, so flank wear में कोई दिक्कत तो नहीं है, any problem? See, suppose earlier you are having the tool like this. Okay, earlier you are having a tool like this, and you are machining it. Okay, so when you are machining, this is how the chip will move. Okay, this is how the chip will move. Now see, when when your tool, when your flank wear is there, when your flank wear is there, then what will happen? So earlier you were able to do this. Now due to the flank wear, your flank size will get reduced. Okay, your flank size will get reduced. So suppose now your tool is something like that. Okay, so now your tool is something like that. So due to this you will have a less amount of material. Due to this you will have a less amount of material removal. Okay, suppose you will have this much amount of material removal. So the chip that will be removed is something like this. Okay, so you can see the consequences of the flank wear. So earlier this is suppose this is of a stage 1 earlier, and this is 1 can be written as before flank wear, and 2 can be written as after flank wear. Okay, because after wearing its size get decreased. Okay, size gets decreased. So due to this flank wear, the amount of chip that is removed got less. Okay, so amount of chip removed lowers down. Okay, clear? So these are the consequences of decreasing the flank wear. When your flank surface get eroded, get weared out. Okay, so these are the consequences of flank wear. Let's see. So what are the reason? So flank wear is also known as wear land. Okay, so what are the reason of the flank wear is that abrasion by hard particles and inclusions in the workpiece. Okay, so what happens, please understand. So when you are machining a workpiece, suppose when you are machining a workpiece, and you have a tool. So understand what will happen. So abrasion by hard particles, what happens? See, in the workpiece, there might be a condition in which some hard particles, any hard particles in that workpiece may get. Okay, so any hard particles may exist on the workpiece, and that hard particles maybe some inclusions also. Okay, so what happens when you are machining, when you are giving some velocity v and machining, a time will come when this tool will get interact with these hard particles. Okay, so get interact with these hard particles. Okay, and these hard particles, what will they will do? So suppose this is your tool, and suppose this is the hard particles. So tool is moving, tool is moving, tool is moving. A time will come when this hard particles get interacted with this tool, and all of a sudden this hard particle provides a shock, and this shock results in the wearing of the tool. Okay, this shocks results in the wearing of the tool. So due to this abrasion, takes place. Okay, so this is a wear mechanism. Let me write clear. So abrasion is a wear mechanism. So abrasion is a wear mechanism. Clear? Next is shearing of the micro welds between tool and work material. What happens when chip is moving, right? When chip is moving and the tool is also moving in the velocity v, a time will come at this point. See, at this point, at this area, what happens? Some micro welds form between the tool and the chip, between the tool and the chip, between the tool and the workpiece. So some micro welds form. Okay, and these micro welds get sheared, and hence the wear of the tool takes place. Next is your abrasion by fragments of built-up paste plowing against the clearance face of the tool. At low speed, flank wear predominates. So this is the one most important thing, that at low speed, flank wear will be more. And if MRR is increased, flank wear will increase. Next thing is there, flank wear directly affects the component dimensions produced. Okay, so this is the first point. Flank wear directly affects the components dimensions produced, and you have already see how the flank wear can affect the components dimension produced. See, earlier the dimension produced was like chip movement was more. Okay, am I audible to you? Am I audible to you? Please let me know. Okay, okay, I don't know what just happened. So see, we were talking about the flank wear. So पहले का सब ठीक है ना? कुछ कुछ प्रॉब्लम तो नहीं हो गया, ऐसा तो नहीं हो गया जो समझ में नहीं आया? Anything? I was explaining and all of a sudden some discrepancy happened. Please let me know. Start from previous two slides. From where? From this flank wear effects. Okay. Okay. See. Okay. See. In flank wear, what are the effects of the flank wear? See, the first point is flank wear directly affects the component dimensions produced. Yes, I am repeating. Okay, see, flank wear directly affects the components dimensions produced. How it directly affects the component dimensions produced? See, we have seen here in this what happened. This is the, suppose before the flank wear and after the flank wear situation is there. So when before the flank wear, amount of chip removed from the workpiece was more, but after the flank wear, see, after the flank wear the amount of chip removed is less. So it directly depends, so it directly affects the component dimensions produced. It depict it actually signifies that how much dimensions of the chip get removed or how much of the dimensions of the workpiece get formed. These things depends on the flank wear. Clear? Next is flank wear is usually most common determinant of tool life. So to predict the tool life, to analyze the tool life, flank wear is very much important point. Clear? Clear to everyone? Now see, flank wear occurs in three stages of varying wear rates. So basically flank wear occurs in three stages. So what are the three stages? First stage is primary. Okay, primary stage. Second is tertiary. Second is secondary. Secondary stage. And the third is tertiary. So these are the three stages in which you can see these three stages in the graph. I have pointed these things with the numbers 1, 2 and 3. So in this y-axis flank wear is plotted and the x-axis time is plotted. So based upon the time, how the flank wear varies and in which are the stages, what is the significance, let's study in this slide. See, primary wear, the reason where the sharp cutting edge is quickly broken down and a finite wear land is established. So see, in primary wear, which is the first stage, sharp cutting edge is quickly broken down. So in this in this in this in this cutting edge broken down. Okay, so in this cutting edge is broken down. So this is the primary stage. Next, in secondary stage, the reason where the wear progresses at a uniform rate. So in this wear progresses at uniform rate. Okay, and in tertiary, the reason where wear progresses at a gradually increasing rate. In tertiary region, wear of cutting tool has become sensitive to increased tool temperature due to high wear land. Regrinding is recommended and before they enter this region. So see what happens in this wear gradually increases, and most important point is there that see, wear of cutting tool gets so much sensitive due to increase in the temperature, right? So due to the increase in the temperature, the wear is so much, and hence regrinding of tool is important. Regrinding of tool is important. तो टूल को क्या करना होगा सर? टूल को रीग्राइंड करना होगा, टूल का धार हमको फिर से डालना पड़ेगा, बिकॉज एट दिस पॉइंट sharpness of the tool get decreased. Clear? So this is, in this regrinding is required. Okay, So basically, three stages of the flank wear is there. First is the primary stage. Okay, so in the primary stage, what is happening, sir? In primary stage, cutting edge is broken down. Next stage is, sir, next stage is your secondary stage. Next stage is your secondary stage, and in the secondary stage, wear progresses at a uniform rate. Okay, third stage is your third stage is your tertiary stage. Tertiary stage, and in this tertiary stage, wear gradually increase and regrinding is required. Okay, yes, yes, Indrajit, sharpening of the tool will is required. So basically this was the story of a flank wear. ये कहानी थी फ्लैंक वियर की. ठीक है, तो फ्लैंक वियर की कहानी में कोई तकलीफ है क्या आपको? फ्लैंक वियर की कहानी में कोई तकलीफ है आपको? See, see, Indrajit has told that if the cutting edge is broken at this point, why we do not go for the regrinding? See, Indrajit, at this point, the cutting edge starts breaking down. It is not completely broken down. It is not completely broken down at this stage, but yes, the wear starts at this stage. So see, there is a cost associated with the regrinding. So always the operator thinks that how should I manage the cost? See, once the cutting edge will get broken down, definitely that tool will be going for the regrinding. That's for sure, that's for sure. But see, today I will send it for the regrinding, or should I use this tool 10 days and after then I will send it to regrinding. So these things depends on the basically for the operators, and based upon that they decided the three regions, and based upon that they go for the at the tertiary stage they go for the regrinding to save the money, to save the economics. Okay, this is from the economical point of view. Got it or not? So any doubt till now? Okay, so kindly solve this question, ESE 2014. So in this question it has been asked the fatigue failure of a tool is due to. The fatigue failure of a tool is due to. Can you tell me what are the reasons that is going to affect the fatigue failure? Okay. C. You are giving the wrong answer. Anybody else? Okay. See. See here. In fatigue failure of a tool. So in machine design, what you have studied, what is the fatigue, or in strength of materials, you may be studying the fatigue thing. What is this fatigue? सो फैटीग क्या होता है सर? फैटीग मतलब हिंदी में अगर मैं इसको बोलूं, थक जाना. थक जाना, थकना को कहते हैं फैटीग. So in terms of mechanical engineering, fatigue means that due to a lot of loadings, stresses and everything, material gets fatigued. So these things are due to variable thermal stresses, chip breakage. So keep in mind that parameters which can produce cyclic stresses on tool, these is important. So you just have to see the parameters are which can produce the cyclic stresses on tool, and this is basically these things are leading to fatigue. These things are leading to the fatigue. Clear? So variable thermal stresses, chip breakage and variable. So see in this everything is there. So option B is your correct answer. Next is ESE 2010 question. Tell me the answer. Tell me the answer. Flank wear occurs on. So on which surface flank wear occurs? Okay. So I'm getting a lot of answers. So this is very easy question. In relief face of the tool, flank wear occurs. Clear? Next question, it has been asked in 2007 and in 2016, in both the years. So flank wear occurs mainly on which of the following? Tell me the answer. फ्लैंक वेयर जो है सर, इनमें से किन किन जगहों पर होता है? टेल मी द आंसर. Subham Raj, you are telling the answer of okay, okay. I understood. My video is actually lagging, right? Okay. So I got answer from Syam. Tell me the answer. Yes. See, flank wear actually occurs on the, see, top face is there. So top face cannot be there. Okay. Only on the cutting is no. See, face of the cutting tool, no. Face of the cutting tool will not be the answer. Nose part, yes. Front relief face, yes. Side relief face, yes. So this is going to be your answer. Okay. So this is the answer. Next, cutting tool is much harder than the workpiece. Yet the tool wears out during the tool work interaction. Because. Tell me the answer. So this is the answer when you will know the wear mechanism. Wear mechanism, then you will be able to answer this question. Okay, so take this screenshot and add this question in your practice question bank. Okay, next, now see, this question can be solved. Consider the following statement. During the third stage of a tool wear, rapid deterioration of the tool is takes place because of which of the following? Tell me the answer. Tell me the answer. Okay, Mukta has told the answer of C. I think you are telling about the previous question. So, yes, that is correct. But once you will understand that wear mechanism, then you will be more comfortable to tackle those questions. So that's why I left that question. Okay, C. No, see, what is asked in this question? What is asked in this question? In this question, it has been told that during the third stage of tool wear, okay, rapid deterioration of tool edge takes place. Rapid deterioration of tool edge takes place. So why this happens? See in this third stage, wear gradually increases, right? Wear gradually increases. So can we say that in this third stage, flank wear is more, okay? फ्लैंक वियर जो होगा सर वो बहुत ज्यादा होगा. दूसरा चीज क्या है सर? इन दिस थिंग cutting tool has become more sensitive to increased tool temperature. So there is a increase in tool temperature. Okay, so there is an increase in tool temperature, and this increase is very much, so drastically it get increased. So due to this, see, in this tertiary region or the third stage of tool wear, plank wear is large and temperature of the tool increases drastically. So due to this reason, option B would be there. Okay, now see this question. In this question, this is a GATE 2008 question. During the machining, the wear land, that is H. So this is flank wear. So flank wear has plotted against machining time, that is T, in the following figure. So this is the figure that has been given. For critical wear land of 1.8 mm, the cutting tool life in minutes will be what? Okay, so try to solve this question. This is a basic, easy question is there. Just use your mind and you will be able to solve this question. Acha, can you tell me what is the logic to solve this question? What should be the logic to solve this question? Or what should be the step to? Yes, Asis has given a hint by using a straight line. See all of you, see, for point 8 and 10. So this is the one coordinate that we are getting, and the another coordinate that we are getting as, see, this is going to be 10 comma point 0.8, one coordinate. Another coordinate that we are getting is 60 comma 2. And now critical wear land is your 1.8 mm. So in this condition, suppose this is your 1.8 and correspondingly 1.8, you will have some time. Okay, so by using this straight line you can find this. So the coordinate, this t you do not know, so t comma 1.8, and when you will solve this, you will get the answer of t, that is the take. Clear? Try to find it and tell me the answer. Yes, Asis, it is right. So firstly try to find the slope, and then with the using the equation of straight line you can find the answer. What would be the slope? See, slope would be 2 minus of 0.8 by 60 minus of 10. Okay, so this is your slope. Fine. Now when you will apply the straight line equation, you will get as, you know, किन्हीं का भी आंसर अभी तक नहीं आया, सिर्फ आशीष जी का आंसर आया अभी तक. Please try to solve. It's a very easy question. See, no problem. So when you will apply, then 1.8 minus of 0.8 by x minus of 10 is equal to m, and m is what? 2 minus of 0.8 by 60 minus of 10. Okay, so from here you will get the x value, and x would be something around 51.666. And what is this x, sir? So this x is your t, so t would be 51.677. Okay, okay, there should not be any confusion with the symbols. Okay, now I am going to teach you the crater wear. Okay, now I am going to teach you the crater wear. यहाँ तक कोई दिक्कत है? Any confusion, any doubts? Then please ask me. Otherwise, I am going to start the crater wear. Yes, option B is going to be your answer. Yes, correct. Syam Mukta, correct. Okay, okay. So I got a reply that everything is clear. So see, now we are going to see the crater wear. So we know that on a flank surface, whatever the wear will there, so that is known as crater wear. Why it is known as crater? Crater, sir, the wear looks like a crater. Wear looks like a crater, and hence the name is crater wear. So see, more common in ductile materials. So it is more common in ductile materials which produces continuous chip. So what is the most important point is there, sir? It produces in ductile material, and in ductile material we have already seen in chips lectures that ductile metals generally produce the continuous chip. A crater wear occurs on the rake surface. So this is understood. This thing is understood. Now at very high speed crater wear predominates. At very high speed crater wear predominates. So see, high speed is for crater wear, and for flank wear low speed is there. Low speed is there. So can you relate those things? In flank wear, low speed will be there, flank wear will be there, and high speed will be there. Then rake surface में problem होगा, and in that rake surface crater wear will there. Next is for crater wear, temperature is main culprit, and tool diffuses into chip material, and tool temperature is maximum at some distance from the tool tip. So what is the most important point is, note the most important point is that crater wear crater wear always starts at some distance from the workpiece. Okay, from the workpiece. So crater wear always starts at some distance from the tool and chip. Okay, tool and chip, because at the at that point, tool and chip interface temperature is maximum. Okay, so क्या sir, at that point tool and chip interface temperature is maximum. So this is the reason why crater wear always starts at some distance from the tool chip interface. Okay, so most important thing is that temperature के ही कारण होता है sir. Temperature is maximum, high speed is there, ductile material will be there, and in the case of continuous chip. So these are the some of the things. Now see, please see one most important graph. So suppose this is your crater wear and this is your time. So when you will plot the crater wear with respect to a time, it will increase like this. So there will be a straight line. Okay, now if you will increase if you will increase the MRR, then the crater wear will look like this. Again, if you increase the MRR, then again crater wear will look like this. So suppose this is MRR, and in this direction MRR is increasing. Okay, so you can understand that crater wear increases with the material removal rate. Okay, crater wear जो है सर material removal rate के कारण बढ़ेगा. ठीक है. So the first point is there, it increases with MRR. It is with MRR. Clear? So this is the thing, that it increases with the material removal rate. Clear? Okay or not? Suppose this is 1, this is 2, and this is 3. So suppose MRR at 3 point is more, MRR at point 2 is this, and less is this. Clear? So based upon that, it increases with material removal rate. Next is crater depth exhibits linear increase in time. So this we have seen already. With this we have seen that there is a linear increase in the time. Crater wear has little or no influence on cutting forces, workpiece, tolerance, or surface finish. So this is the important point. So this is all about the story of the crater wear. See, in high speed, what happens, Kiran? In high speed, the temperature at that point get increased. The temperature at that rake surface get increased. And see, due to the increase in the temperature, there are the wearing. And we are going to see some of the wear mechanism, and in that wear mechanism you will get a clear idea that only one parameter is sole is not important or not deciding factor to wear that tool. Clear? Only one parameter is not whole and sole to decide that, sir, due to this parameter tool wear will be there. Okay, so you will be understanding when I will discuss the wear mechanism. But I hope you got the answer that temperature at that rake surface get increased. Okay, so due to that there is the wear. Mukta has given answer C. Okay, tell me the answer of this question. Tell me the answer. See, I have just explained you. The crater wear always starts at some distance from the tool chip because due to the tool and chip interface temperature is maximum. Okay, so temperature is your maximum, and due to this reason the crater wear on the tool always starts at some distance from the tool chip interface. And let me tell you, this question has been also asked in GATE. Okay, I don't remember the actual year, but yes, I could remember that this question was asked in GATE also. Okay, next, tell me the answer. Same thing is there. Tool temperature is maximum in that region, right? So see, different examinations ask this question because this question is one of the conceptual question, and once everything is there, understandable to you, बन जाएगा सर सब क्वेश्चन, that's okay, बन जाएगा सब क्वेश्चन सर. Next, see again, EEC 2000. So what is that in this question? Crater wear starts at some distance from the tool tip because tool temperature is maximum at that region. Clear, sir? So see, back to back same questions in different. It has been asked in GATE. It has been asked in ESE 2000 IAS. So see, same question is there, and it has been asked at multiple places. Till now, everything is clear to you. As I'm going to start a new subtopic, mechanism. Wear mechanism. Out, then please tell me, or I will start the new topic, wear mechanism. Okay, so I assume that you don't have any doubt since you are not telling to me. So I assumed you don't have any doubt. Okay, see, so now we are going to discuss what are the wear mechanisms that are involved in this tool wear. Okay, so first is your abrasion wear. First is your abrasion wear. What happens in the abrasion wear we are going to see at the latter stage. Next is your adhesion wear. Next is your adhesion wear. Third is your diffusion wear. Fourth is chemical or oxidation wear. Okay, so let's see one by one the wears. Diffusion wear. What happens in the diffusion wear? See, that this is a tool. Okay, this is a tool. In this tool there are a lot of hard materials are there. Okay, so suppose in this tool carbon particles are there. In this, carbon particles are there. So now what happens that in this tool is made up of carbon and other materials. Okay, and other materials. Okay, so these materials are like what? High density materials. Okay, high density materials such as carbon. Okay, so this is the tool. This is the story of the tool. So tool is made up of some carbon or other materials that are high density, which is more specifically that is carbon. Okay, now see, to excessive temperature. So due to excessive temperature at that chip and tool interface, what happens due to the excessive temperature at shear zone, high density particles from tool gets go to the chip. What happens from the tool? High density particles go to the chip. I'll explain. That is the carbon particles. That is the carbon particles. What happens that carbon particles move to the chip. Now see. Now see the condition. What is the problem? My audio video is clear to you or not? Not. Why the hell there is so much of problem? Okay, okay. Sam is telling me that my audio video is clear. Okay, fine. See, so कुछ छूट गया क्या? What I was explaining till now, everything is clear to you, or should I explain these things once again? I don't know. There is some network issues, and this is creating the problem. Till now, everything is okay, or should I re-explain these things once again? Kiran sir, I will be confusing when I study wear mechanism. Is it related to material science or is it different? See, Kiran, this is actually, this is actually, you can say, basic of manufacturing, right? You cannot say this is of material science, and material science, everything is like different. So, okay, so yes, I'm explaining these things once again. Okay, I'll explain these things once again. See, so see, this is a tool. Okay, this is your tool, and this tool is made up of carbon and other materials, right? That is, those materials are high density materials such as carbons, right? So what happens due to excessive temperature at secondary shear zone, high density particles from tool will go to the chip. That is, carbon particles move to the chip. Now let me draw the figures. Now you will understand everything. Suppose this is your tool. Suppose this is your Clear? Suppose this is your tool, and in this tool, this is the chip. Okay, so this is the chip. Clear to you? This is the chip. Now what I have told to you, I have told to you that in the tool there are some of the hard materials, right? Clear to you? So what happens that carbon particles at the high temperature moves like this, moves like this, moves into this, moves into this. So the resultant picture will look like what, sir? The resultant picture of this tool will look like this. So what will happen that this carbon particles will move to the chip, and hence when it moves to the chip, it simply means that tool becomes weaker. Clear? Clear or not? How tool is becoming weaker? Due to this diffusion mechanism. So due to this diffusion mechanism, so just in what is the gist, carbon particles moves to the chip. Okay, let me write it. Carbon particles moves to the chip due to the high temperature. Okay, so this is the basic thing, and due to this, tool weak, tool weak. Okay, so weakness in the tool, better to write weakness in the tool, weakness in the tool. So clear? Okay, so I got the answer from you, everything is clear. So this is the story of the diffusion. Okay, so this is the story of a diffusion. Now next is your adhesion. Next is your adhesion. Next is your adhesion. So what happens, so let me tell you one thing. What is the key takeaway point from this? We have seen diffusion wear is due to the molecular transfer. Diffusion wear is due to the molecular transfer. Clear? Diffusion wear sir क्यों होता है? This is only because of molecular transfer. What is the molecular transfer, sir? Carbon particle, that particles is the molecule, and this molecule get transferred to the chip, So this is the phenomena. Next is the adhesion. Now see what happens in this adhesion. At high temperature, produced at chip tool interface, shearing action of chips takes place. Okay, and due to this chips get welded at tool, that is called as adhesion. What happens here, that at high temperature produced at the chip tool interface, shearing action of the chips takes place, and this chip get welded at the tool. Suppose this is your tool. Okay, suppose this is your tool and this is the chip, and this is the chip. So what happens, the part of a chip get welded. Suppose at this point it is micro welded, at this point it is micro welded, at this point it is micro welded. So sometimes what happens, this micro welding takes place, this micro welding takes place, and that part get adhesed, right? Due to the adhesion, micro welding takes place. And what will happen once the part get micro welded? So after the using, whether that part will erode the tool or that part will stick to the tool. Clear? That chip part, whether that chip part will erode the tool or that chip part will stick to that tool. So in both the cases, the wearing of the tool takes place. Yes, Kiran, right. Built up edge is also because of adhesion. Yes, correct. So this is the thing in adhesion, right? This is the story of the adhesion. Now I'll explain the. I have to take some slides. So now I'm explaining you the abrasion. I don't think that you have any doubt till now, because I'm explaining very slowly as well as very neatly. So you should not have any confusion. But even if you have any confusion, let me know. Abrasion. Next wear mechanism is your abrasion. Okay. So one most important thing is there. So what is the key takeaway point from this adhesion is that there is a formation of metallic bond. There is a formation of metallic bond in adhesion. Clear? So what is the thing that we are learning? Slowly and slowly, what are the things that we are learning? That this is due to the molecular transfer. Due to the molecular transfer, diffusion wear is there, and due to the metallic bond, this adhesion takes place. Clear? Next is your abrasion. Now see, I have already told you, see in this question when I was discussing with you, let me find that question. See, when I was telling to you the flank wear, so in this flank wear, this one thing was there, abrasion by hard particles and inclusions in the workpiece. Hard particles and in the workpiece. What is the meaning of that? I have already explained at that time, but let me explain you once again. Hard particles and inclusions are there in the workpiece. So suppose this is your workpiece. Okay, suppose this is your workpiece. Okay, and this is the tool, and this is the tool. Okay, so this is the tool, and in this workpiece some hard particles are already present, and in this workpiece some hard particles are already present. Let these things to be the very hard particles, that is carbons or inclusions. So these are like what? These are your hard particles plus inclusions. So what will happen when you are giving the velocity v? So when at a time will come that these hard particles get interacted with this tool and this hard particle will impart a shock, in this workpiece, and hence there is a sudden shock, and due to this sudden shock abrasion would be there. And this, suppose this is your tool, so earlier this was your tool structure, and when the abrasive particle will strike it, the tool structure will like that, it will damage the tool drastically. Okay, so 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 suppose the hard particles are sometimes like nickel are also there, carbon are also there. So these type of particles are also present during the abrasion. So see, you can see that this, what happens, that some that particle, that abrasive particle, that hard particles erode this part, like see, take out this part and move away. So it takes this part and tries to move this part away from the tool. So you can understand, and this is something which is plowing action. Okay, so this is something which is of plowing action. क्या होता है सर कि टूल यहाँ पर है हमारा, ये टूल हो गया सर, and from this tool surface what will happen, this is suppose the rake surface of a tool, and this abrasive particles क्या करता है सर, वो आता है, चीजों को उखाड़ता है और उखाड़ के लेके चला जाता है. So what does it, that at a sudden it gives the load, it gives the part, and this rake surface get eroded, and this is the plowing action of the abrasion mechanism. So clear? So this is the logic behind the abrasion. Next is your chemical oxidation. Next is your chemical oxidation. So what happens, that at high temperature air reacts at secondary shear zone. Okay, and form a oxide layer which makes the tool weaker. So what happens here, due to the chemical oxidation, due to the high temperature, so due to the high temperature, air reacts at secondary shear zone and it forms the oxide layer. And due to this, the tool becomes weaker. So this is the thing, this is the whole mechanism of wear mechanism. So this is the wear mechanism number 4, what we have learned. This is the wear mechanism number 3, this is the wear mechanism number 2, and this is the wear mechanism number 1. So these are the wear mechanisms, and I have explained these wear mechanism in great details, and I don't think you will be having any confusion till now. So please tell me the answer of this question. Please try to solve this question and give me the answer. Please try to solve this question and give me the answer. These questions are based upon the concepts what I have told to you. So you will be able to attempt this question. I want the answers from everyone. Yes. So we have studied that tool wear is due to these things. Mechanical abrasion is there, diffusion is there, and oxidation is there. So there is no question about plastic deformation, right? So option would be C. Okay. Next, try to solve this question. Try to solve this question. Try to solve this question. I have been given a lot of options, so let us see. Abrasive wear. Abrasive is wear is due to what, sir? So see the previous slides. What I have told to you. Abrasive wear is due to the plowing action. Is due to the plowing action. Clear? So 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 abrasive wear is due to the plowing action. So A will be 2. Clear? A will be 2. So option B and option D will be wrong. Okay, because in option A option has the 2 and the C option has 2. Next is your diffusion wears. Okay, so diffusion and adhesive wear, what we have studied, see here. In diffusion, in adhesion, metallic bond is there, and in diffusion, molecular transfer is there. In diffusion, molecular transfer is there, right? So where is the molecular transfer? This is 3. Okay, so this is 3. And adhesive wear, what we know about the adhesive wear? We know about the adhesive wear is due to the metallic bond. So metallic bond. Now by only seeing the 3 options, we can see A will be 2, B will be 5, and hence this is wrong. This is going to be your right answer. Clear? क्लियर है सर? बहुत अच्छे तरह से मैं पढ़ा रहा हूं, ध्यान से पढ़ेंगे तो आपसे सब क्वेश्चन बन जाएगा. You will be able to solve every questions. Next is this question. Try to tell me the answer. The type of wear that occurs due to the cutting action of the particles in the cutting fluid is referred as. Just take these things as for your homework, right? For the practice, because I want to introduce some new concepts. Okay, I want to introduce some new concepts. Now see, this is the Taylor's tool life equation. Okay. See Indrajit, what is the problem? Suppose suppose how the oxide layer is making the difference here. Suppose this is your workpiece, and this workpiece is coated with the oxide layer, and this oxide layer is very hard, very brittle. So what happens? Suppose this tool, when tool will try to machine this surface, all of a sudden the tool will encounter the very brittle material, very brittle material, hard material, due to the formation of that oxide, and due to this abrupt force will come to the tool and tool will get fractured, tool get failure. Okay, so got the things or not? So now, see, tool life, depends upon various things. Tool life depends upon various things like time of machining. Okay, time of machining. Next is your number of parts produced. Number of parts produced. Next is length of workpiece machined. Length of workpiece machined. Next is your volume of material removal. Okay, material removal. So it simply means that MRR. Okay. Next point is your RPM. Your RPM of the tool. So these points are there to which really affects the tool life. Which affects the tool life. Okay. So these are the points which affects the tool life. And so actually a scientist was there that whose name was Taylor, and Taylor scientist has given that बच्चों ये आपके लिए है, एक मैंने इक्वेशन आपका डाल दिया. So Taylor sir did a fantastic job, and in that job what he did, he just given a relation between the cutting speed and the time, tool changing time. These things are there. So V is the cutting speed which is in meter per minute, T is the time which is in minute, N is the exponent depends on the tool material, and C is the constant based on tool and work material and cutting conditions. So here the constant C changes for the different tool and the work material. So this relation is called as Taylor's tool life equation. Okay, and basically this is based on the flank wear, so sliding of tool along the machine surface is there, and temperature rise we have already seen. So these are the causes due to the flank, these are the causes due to this flank wear actually happens, and due to this, based upon these reasons, Taylor has given this beautiful equation Vt to the power n is equal to constant, in which these V, T, N and C have their as usual meaning whatever is being mentioned. Okay, so having understood these things, as I have told you, the value of C will vary based upon the tool and the work materials and the cutting conditions. So kindly see it here. So value of the exponent n, that is the n, will be 0.08 to 0.02 for high speed steel. For cast alloy, the exponent will be 0.1 to 0.15. For carbide, it would be 0.2 to 0.4, and for ceramic, it would be 0.5 to 0.7. And these are the exams in which these data has been asked directly. In IS, in ESE, the exponent value for the carbide tool has been asked, and in NTPC, the ceramic exponent value of the ceramic tool has been asked. Now see, one more observation I want to tell you, that you know that V t to the power n is equal to constant. Clear? So now if I will say that V1 t1 to the power n is equal to V2 t2 to the power n. Now sometimes what happens, you have to find the n. So you have to find the n. So how you can find the n? So I am just making the equation very simpler to you, so that whenever you will encounter this problem, to find the n, you just use this equation and your life will be okay. So see, if in both the sides, if I will take the log, that is the ln, so n ln t1 by t2 is equal to ln v2 by v1, and from here you will get n is equal to ln of v2 by v1 of ln t1 by t2. Clear? So this is the equation to find the n. Okay, so till now everything is clear to you? Just give me a thumbs up if everything is clear to you, whatever I have explained to you. Otherwise I'll take your doubt. Tell me. Clear? Okay, so great. So these things are very much important for your gate point of view. This equation is very much important for your gate point of view. Let me tell you, this is very much important for your gate point of view. Okay, for your gate point of view this is important. For your gate point of view this is important. Okay, so now here is your question for you, the beautiful, the best question asked in ESE 2012. Tell me the answer. Tell me the answer. Try to solve this question. This question is very easy. It has been asked in ESE in the year of 2012. Tell me the answer. Okay. Could you check your answer? Mukta, Asis, both of you. Hmm. See, see everyone, what is the logic? See, we can see here, we can see here this term. What is the term? Cutting condition. Okay, work material and the tool. So Taylor tool life equation depends on the tool, depends on the work material, and depends on the cutting condition also, except velocity and the time. Time और velocity के को छोड़ करके सर टूल, वर्क मटेरियल और कटिंग कंडीशन तीनों पे भी डिपेंड करता है हमारा टेलर टूल लाइफ इक्वेशन. सो व्हाट वी कैन सी in from the cutting condition, the coolant, the use of the coolant is actually comes under the umbrella of cutting conditions. What should be your cutting conditions? And hence this work material is important, tool material is important, and the coolant is also important. So in Taylor's tool life equations, Vt to the power nc, constant nc depends on these three things: work material, tool, and coolant, and hence option A is going to be your answer. Clear, sir? Clear, sir? These questions are very confusing. You will get confused very easily. But the logic is that, sir, you have to understand each and every words what I have given to you. आप एक एक वर्ड्स को सर अच्छे से देखें. अच्छे से देखने से आपको खुद पता चल जाएगा कि what is the significance of tool, work material, and cutting conditions, what has been written here. Okay, and these things really determines the how you solve the question. Now please solve this question. There is another question. Kindly try to solve this question. ESE 2008 question is there. In Taylor's two life equation, Vt to the power n is equal to constant. What is the value of n for ceramic tools? Okay, so see here, for the ceramic tools, its value is 0.5 to 0.7. Okay, so its value is 0.5 to 0.7. So what should be your answer? Tell me what should be your answer. The value is 0.5 to zero point 0.7. Now see the answers in this options which is coming under the zero point 0.5 to zero point 0.7. So when you will see, the option C is coming under the between the 0.5 to zero point 0.7 range. So option C is going to your answer. No, Sam, option B will not be your answer, because see, you have to choose your option which uh, which actually includes this range 0.5 to zero point 0.7. Okay. Now again, for the cemented carbide, what would be there? So these things are for your practice. For cemented carbide, what are the things would be there? Now here comes the question. Good question. Try to solve this question. Try to solve this question. I am giving you the 2 minutes time, and within this 2 minutes time, try to solve this question. Okay. Okay, you are giving the answer of option C. Okay, fine, that's okay. Now please try to solve this question. Please try to solve this question. Try to solve this question. Hmm. Answer is A. Answer is A. So this is the easy question, but yes, let me tell you once again that this question might seems to you easy, but this is how the these questions are asked in GATE. Okay, in GATE you will encounter these types of questions, so which are very easy. Believe me, very easy. So see, earlier this is the time which is given. So T1 is given as 10 minute. Cutting speed is given as 100 meter per minute. So V1 is given as 100 meter per minute. Next is what? Your 75 meter per minute is given as V2. So V2 is going to be your 75 meter per minute. And the tool life is your 30 minutes. So T2 is your tool life, and that is your 30 minutes. So now how you can find the n? So by using the Taylor's tool life equation. And what is the Taylor's two life equation, sir? Taylor's two life equation is Vt to the power n is equal to V2 t to the power n. Just plug in the values, right? Or you can use the formula that I have written here. See this formula, just put the values in this formula and you will get the values. Okay, so just 100 into 10 to the power of n is equal to 75 into 30 to the power of n, and from here n value would come around 0.2618. So that would come around 0.2618. So that is roughly as 0.262. Clear? Clear, sir? Concept is clear, sir? So this is how you can solve the question. Next, kindly solve this question. Kindly solve this question. Kindly solve this question. Try to solve these questions. Asis has given option as C. Okay. Great, Asis. Great. Good. Some more time I'm giving to all of you. See, now I will solve the question. See here, everybody. A 50 diameter steel rod was turned at 284 rpm. Okay. So see, the n value is given as n1 is given as 284 rpm. Okay. And this is the diameter. So since n1 is given as this, so what would be your v1? V1 would be pi dn1 by 1000. Now why 1000? See, because this is in mm. Okay, so what I can write here as v1 is nothing but pi, d is 50 into n is your 284. Okay, by 1000. So this is your meter per minute. The answer would be meter per minute. Clear? Next is your n2. Next is your n2. So the speed changed to 232 rpm and the tool filled in 60 minutes. So earlier there was the T1 is the tool life. And what is the n2? N2 is 232 rpm. So 232 rpm and the velocity 2 would be pi dn2 by 1000. So velocity 2 would be pi 50 into 232 by 1000. The reason why I am doing these things I'll explain once a minute, because there is a trick in here. Trick is involved here, but I'm just explaining these things because there is some reason behind it. So in this case, what is the T1? T1 is your 10 minutes, and what is your T2? T2 is your 60 minutes. Clear? So by applying the Taylor's two life equation, that is V1 T1 to the power n is equal to V2 T to the power n. So in this equation, when you will plug in the values, you will get as pi 50 284 by 1000 into T1, that is 10 to the power n, is equal to pi 50 232 by 1000 into 60. Now see what I was trying to tell. See, in this question you have the option. What is the option you have? You can neglect these things, because ultimately this when you are equating both the things, these things does not make sense, because eventually these are going to be cancelled out. So what you can do, this formula can be reduced to n1 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 t1 to the power of n is equal to n2 t to the power of n instead of this. So you can directly apply this by putting the n1 t1 to the power and n is equal to n2 t to the power n. You can easily solve this question, but the problem is there. The problem is there. Why I have explained this to change the velocity in this, because there might be this tendency. This tendency will uh, improve this tendency will improve your accuracy. Always try to think, whenever this is n, try to find that velocity will be in this direct this things. So अगर क्या होगा, अगर क्वेश्चन आपको थोड़ा सा घुमा दे, थोड़ा सा बदल दे, तो आपको ये दिमाग में रहना चाहिए कि if I have n1, how can I find the velocity? That's okay. In this question, you can solve this by this trick also. Eventually, they are going to be cancelled. But always keep in mind what should be your velocity. Clear? So this is the concept that I want to let you know. Okay. Yes, that's why I have told. That's what I have told here. That's what I have told Kiran, Ashish, Syam. Yes, everybody. So I just try to bring the concepts into what to your face, right? So just it should be a good habit to do things. Eventually you can use this formula also. Okay, now try to solve this question. Try to solve this question. कभी कभी क्या होता है ना सर, फॉर्मूला के चक्कर में हम बेसिक कॉन्सेप्ट को भूल जाते हैं, तो वो नहीं करना है सर. ट्रिक तो हमें ऑलवेज दिमाग में रखना ही रखना है. ट्रिक इज द थिंग दैट विल गिव यू केस ओवर ए लॉट ऑफ कॉम्पिटिशंस. ट्रिक्स तो हमें याद रखना ही रखना है, बट कॉन्सेप्ट्स को भी याद रखना है. ठीक है. So I have got answer from Syam or from Shivam in the GATE option C. Please try everyone. Everyone, please try. See, in this question, the machining operation. In this machining operation, doubling the cutting speed reduces the tool life to 1 by 8. Okay, so you are doubling the cutting speed. So V2 would be twice of V1. Reduces the tool life to 1 by 8th of the original value. So T2 is your 1 by 8th of the original value. The exponent of n would be what? So we can know that V1 T1 to the power of n is equal to V2 T to the power of n. What is your V1? So you can write so V1 by V2 is equal to T2 by T1 to the power of n. So here, from here, V1 by V2 would be 1 by 2. So you can plug in here 1 by 2. T2 by T1 can be 1 by 8. So 1 by 8 to the power of n. You can write 2 is equal to 8 to the power of n, which is nothing but 2 to the power n is equal to 2 to the power of 3n. And by comparing the bases, you can say n is equal to 1 by 3. Okay, n is equal to 1 by 3. Okay, now solve this question. Now solve this question. Now try to solve this question. Okay, so everyone is giving the answer as C. Okay, let me check it. No, you all are giving the answers of previous questions? I think so, because this is not the option. What we will take here, value of n. Okay, so what should be your value of n? See here, Taylor's tool life exponent is 0.25, and this is the n. Assis, this is the n. Okay, Kiran, answer is wrong. Indrajit, answer is correct. Correct answer is there. You have given correct answer. See, I'll explain this question once again. There is a single point turning operation of steel with a cemented carbide tool. Taylor's tool life exponent is 0.25. So Taylor's tool life exponent is 0.25. And if the cutting speed is halved, so if the cutting speed is halved, the tool life will increase by, then they are asking that tool life will increase by how much amount of T1. Okay, in this question this is what is asked, so try to solve it. I don't think there is a problem, so you just need to find the T2 by T1 will be what. This is the thing that you have to find. I hope question is clear to you. And see, these questions are very basic questions. Directly these are related with the Vt to the power n is equal to constant, which is our famous the Taylor's tool life equation. And if you are well conversant with this equation, you can solve this question. These questions are asked in ISRO, ESE, GATE, in every examinations, whether you are talking about SSC, JEE, every examination this question is asked. So very easy question is there. Try to solve it. Okay. Okay, then I am solving this question. See, so by Taylor's two life equation, Taylor's two life equation, Vt to the power n is equal to constant. So V1 T1 to the power n is equal to V2 T to the power n. Okay. Now see, V2 is half of V1, so we can write V1 T1 to the power of n is equal to half of V1 T2 to the power of n. So from here we can see this V1 and this V1 get cancelled, and what we are left with, 2 is equal to T2 by T1 to the power of n. Now this n is nothing but 0.25, right? 0.25. So this 0.25 is what? This is 1 by 4. So we can write here as T2 by T1 to the power of 1 by 4, which is equal to 2. So T2 to the power T1 is equal to 2 to the power of 4, which is T2 by T1 is equal to 16. Clear? Clear to you, everyone? This question is clear to you? So option would be your D. क्लियर है सर सभी को ये सारा चीज जितना भी मैंने अभी तक बताया आपको? ओके, सो ये थी कहानी अभी तक की टेलर्स टू लाइफ इक्वेशन की. चलिए एक लास्ट क्वेश्चन ये है गेट 2016 की, इसको भी सॉल्व कर लेते हैं. टेलर्स टू लाइफ इक्वेशन पे बेस्ड है सर. प्लीज ट्राई टू सॉल्व दिस क्वेश्चन. प्लीज ट्राई टू सॉल्व दिस क्वेश्चन. See, I am explaining this question. In a single point turning operation with cemented carbide tool and steel workpiece, it is found that Taylor's two life equation is 0.25 if the cutting speed is reduced to 50%. If the cutting speed is reduced to 50%. So cutting speed is reduced to 50%, that is 1 by 2 of V1. It simply means 1 by 2 of V1. And here n is given as 0.25. Then tool life changes by how much? So see, in this question what we have seen as this. Okay, V2 is equal to half V1, same conditions was there. So in this question, the question has been posed in a different way. Okay, in this question has been posed in a different way. There is nothing new about it, but the thing is the cutting speed is reduced by 50%. Only this much amount of information is different, rest everything is same. Okay, so what I want to clear the concept why I have given this both the questions. So this is the reason, sir, whether it is ESE or it is ISRO, whether the year is 1999 or whether the year is 2013, or whether sir it is a GATE or the year is 2016, all are brothers, right? So these brothers, what they actually do, they take the questions from ESE and put in GATE. They take the question of GATE, put in ESE. They take the questions from GATE and ESE and put in the ISRO. So you have to solve the previous year of this prestigious examination, and once you will solve the previous year of this prestigious examination, no question will be unturned. I repeat, if you will solve the questions, if you'll practice a lot in this manufacturing, I can guarantee no questions will be unturned. I can bet you. Okay, now see this question. Now see this question. Now see this question. In this question, Taylor exponent is 0.25, cutting speed is halved, tool life will be what? Sir, same. Okay, same, same, same. So, so questions style of asking the question may be different, but eventually the concept will same, concept will remain same, and this is why I force you that you have some limited amount of concepts that you have to study in this gate. And if you will practice and practice and re-practice and re-practice the questions, eventually you will solve everything. So this is what is from my side for today's session, and if you have any doubt, then please ask with me. And if you are planning for a plus subscription, you can always use my code SIRVK, in which I can give you the 10% off as well as the mentorship towards your whole gate preparations. Okay, feel free to ask this, use this code. If anyone is in your contact planning to give you to purchase the plus subscription, you will get the 10% off by using this code. Okay, sir, when it will be going to complete? Ashish, like tomorrow I think this tool economics of machining everything will get complete, and after tomorrow I'll start a new chapter. Okay, I'll start a new chapter. Okay, any other doubt? See this metal cutting, see this metal cutting plus uh, machine tools. Okay, so this is the two different chapters. So I think after tomorrow onwards this chapter will be finished, and after that this is the machine tools. In this machine tools would be like lathe would be there, milling would be there, drilling, drilling, and grinding, these things would be there, as well as these all are traditional machining, and then would be there non-traditional machining, and this non-traditional machining would includes like EDM, ECM, AJM, okay, EBM, and these machinings are there. Okay, so this is what is the thing. Machine tools, I will start machine tools or welding, I'll let you know. Okay, because these things are very small, these things are very small. Metal cutting was very big chapter, and this is going to be finished tomorrow. Okay, any doubt? Any doubt? And these are the plus subscription plan. If anybody is interested, for 24 months it would cost around 30,000, but you will get it at a cost of 27,000, and you will get it with help of my code SIRVK. 10% off would be there, and one subscription would give you the benefit of GATE and ESE both. Okay, so I assume that you don't have any doubt. So thank you so much for your active participation. Thank you.